Hello. Today's video deals with application of the mean value theorem, MVT. Mean value theorem says if f is continuous on the closed interval AB, f differentiable on the open interval AB, then there exists some c in the open interval AB where f prime at c is equal to f of b minus f of a over b minus a. Now, again, all of these theorems, IVT, EVT, Rolle's, MVT, they are existence theorems. They tell us something about something existing. And in this case, while this looks more complicated, it's really pretty simple. If I have a continuous function on some closed interval AB, like this, where it's differentiable, in other words, it's nice and smooth, then f of b minus f of a over b minus a, this is the point a comma f of a. This is the point b comma f of b. And so this f of b minus f of a over b minus a you might recognize as the slope of the secant line. If I could draw this, the slope of the line that goes through the two endpoints. And what Rolle's theorem says, what mean value theorem says is that there exists some point C, at least one, where the derivative at that value is the same as the slope of the secant line, the derivative being the slope of the tangent line, and so there's some point C, in this case there's actually two, where the slope of the tangent line is the same as the slope of the secant line through the two endpoints. Something like this. Again, forgive my drawing, but there's two such values in this case. We're guaranteed at least one. That's what mean value theorem says. Mean value theorem has a lot of applications that are kind of hidden. We are just going to look at a couple here. So the first one being, and again this is a problem that's worked out in the exercises, number 6 I believe. Find all C guaranteed by the mean value theorem for f of x is equal to x plus arctan of x on the interval from 0 to 1. Okay? So this function is continuous everywhere, differentiable. So let's take the derivative. F prime of x would be 1 plus 1 over 1 plus x squared. That's the derivative of arctan. And MVT says f prime at c, let me write up the conclusion, is equal to f of b minus f of a over b minus a. Literally, let's plug in values. F prime at c would be 1 plus 1 over 1 plus c squared, and that's equal to f of b, 1 plus the arctan of 1 is pi over 4, minus f of a, the arctan of 0 is 0, over b minus a, which is 1 minus 0 or 1. And so therefore, 1 plus 1 over 1 plus c squared is equal to 1 plus pi over 4, which means that 1 over 1 plus c squared is equal to pi over 4. And so therefore, 4 is equal to pi times 1 plus c squared, or 4 over pi is equal to, well, let me distribute this out. 4 is equal to pi plus pi c squared, or 4 minus pi, do it this way, is equal to pi c squared, and so therefore c squared is equal to 4 minus pi over pi, or c would be plus or minus the square root of 4 minus pi, 4 minus pi divided by pi. Now, because I'm dealing with the interval from 0 to 1, even though there are two solutions algebraically, there are not two values of c in this particular case. The only actual values for c that we get is the square root of 4 minus pi over pi, whatever that comes out to be. Numerically, you can figure out with a calculator. Another application of MVT. Let's suppose that I have the following. Suppose I want to use MVT to show if 3 is less than or equal to f prime of x is less than or equal to 4 for all x, then 15 is less than or equal to f of 5 minus f of 0 is less than or equal to 20. Now, seems like this doesn't really fit the situation that we dealt with in terms of MVT. Let me write up the conclusion for MVT again. F prime at c, there exists some c in the interval. Well, c in the interval AB, I'll put it that way. F prime of c is equal to f of b minus f of a over b minus a. Now, if I want to deal with this that I'm given, somehow using IVT, we look for something that looks similar. And notice this f of 5 minus f of 0, and over here I have f of b minus f of a. And so let's use MVT on the interval from 0 to 5. Since the function is differentiable, it always has a derivative between 3 and 4 for all x. MVT applies, so we're okay. We'll consider the interval from 0 to 5. Then, by MVT, we know there exists some c in the open interval from 0 to 5 where f prime at c is equal to f of 5 minus f of 0 over 5 minus 0, or just 5. This means that 5 times f prime at c is equal to f of 5 minus f of 0. Now, this is where we use this piece of information here. 3 is less than or equal to f prime of x is less than or equal to 4 for all x. C is some particular x value. I don't know what it is, but that's okay. We know f prime at c is between 3 and 4. So 5 times f prime of c is going to be between 5 times 3, and I wish I could write, and 5 times 4. Or, in other words, 15 is less than or equal to 5 times f prime at c, less than or equal to 20, since f prime at c is f of 5 minus f of 0, we get exactly what I wanted to show.